Now after we've seen how networking works with Docker, we're going to talk a bit about networking and about high availability in networking. So I'm Berezin, Senior Technical Product Manager with Red Hat. Today I have Livnat Pierre with me, who is the Engineering Manager for Networking with Red Hat. And so today I'm gonna set the ground a bit about what HA means in OpenStack and the general approach of how most distributions do it today. Obviously, I'm gonna be a bit biased towards Red Hat, but I'm gonna mention what other folks are doing as well, just a bit, and then Livnat will actually deliver the actual meat in the presentation and discuss the various built-in mechanisms within Neutron itself. So you obviously can download the slides from this QR code. I'm going to have the QR code at the end of the session as well. So if you don't get a chance to take a shot of it now, you could do it also by the end in the last slide of the deck. All right. So I really like the analogy of our OpenStack, and when we build an OpenStack in production, this is what we're trying to achieve, right? We're trying to build our Formula One team and basically building the best OpenStack, like real production environment we can get to. And as we all know in racing, there are some things that are extremely important. Hold on, Windows. So yeah, you get the idea. You get the idea that your controller is one of the most important things in your production environment. You have to make sure your controller always works and make sure that what you do with the controller actually controls your vehicle or your OpenStack environment. So high availability, right? When we're building a highly available environment, what we're trying to do basically is minimize the downtime, the possible downtime we have in this environment that we're trying to build. So as you all know, most of OpenStack services are stateless. So but at this point in time, we get a pretty good common knowledge of how to make sure that stateless services that are just present a specific API or just show in a specific provide an external web service, make sure that this service is highly available. It's pretty simple. We have good methodologies to do that, and I'm going to discuss those. And basically, if the service is not stateless, which some of the services with OpenStack are not stateless, we either use built-in mechanisms. So Livnat will discuss the built-in mechanisms within Neutron that we can use to make Neutron highly available and make the Neutron node highly available and the API highly available. And obviously, if there is no built-in mechanism for HA in the service, it has to be active-passive, not to have any concurrency problems, etc. And the Cinder volume service at the moment is a good example for that. A service that unfortunately is can cause some conflict. So the best approach at the moment is just to run active passive. So we've seen this slide I think like a million times. We all know OpenStack is extremely complex beast, and we have to make sure that each of the services is highly available. So I'm going to just talk about the general approach, and then Livnat will dive into the details in Neutron. So we're using two mechanisms that are coming from the operating system itself to basically wrap around the services. So we use the first component, which is Pacemaker. which is a cluster resource manager. Basically, it monitors various services and takes control over them. So it's capable of starting a service, stopping a service, etc. And obviously, it uses systemd and other distros environments as well. It also supports a virtual IP, so I can create a virtual IP for a specific service with Pacemaker and make sure that the virtual IP is bouncing where the service is active at the moment. Or I can set some various policies, for example, round robin, etc. And we'll also have a set of best practices for each of the services in OpenStack services, like which is best to have round robin, which is better to have a statically configured link to each service. And obviously, we also have the support for cloned services, which basically makes Pacemaker to run multiple instances of the same service, which is effectively becoming an active service. Now, the last piece, which is extremely important with Pacemaker, is something called Stateless, which stands for shoot the other node in the head. It's really nice acronym, but what it means is basically I have full control over other nodes. So if I have a node which is not responsive, for example, and I'm not sure, like I'm trying to restart the service on it, right? And the service fails, or like I'm trying to restart the service, but I have no access to the other node, and I'm not sure, like, is he running, is he not running, like is he locking something, etc. So basically, the fancy mechanism triggers a command to the remote control of the server to restart the server. And obviously, this is like the last choice we have to make sure the service's status. So let's go quickly over the flow, over the general flow. So basically, we have Pacemaker, which monitors the services themselves, and we have the virtual IP on top of them. So if a user goes to a specific IP, one of the services is going to provide the service that the API presents, and I can shift, sort of say, the virtual IP and bounce it from one host to another. So the three important things that we're using here. One is the virtual IP, second is the control over the service, and the third is the fencing mechanism. So the second mechanism that we're using in OpenStack, and this is a really general approach that's used, is HA proxy, which does really well, which is a really good load balancer for web traffic and for HTTP and HTTPS types of traffics. It's really well used around in the online and web scale world. A lot of the major players use it, and its maturity is proven over time. So it does two really good things. The first is, well, obviously load distribution. Well, it is a load balancer, right? But the second really good thing that it does is basically a health check for the service. So if a service dies, HA proxy is capable of immediately stopping traffic to that service. So basically, I have like an instant failover to the active node, and the node that failed automatically is trying to recover. So yeah, we've discussed this, and we discussed that there are several policies. So if we go over the flow of both of the services, so for example, I'm trying to get a specific service, and I've in the last second change this to Neutron, but this goes to a Horizon or to any of the API services, which are obviously stateless and classic example of stateless services. So a user asks a request from that server, and that server becomes a single point of failure. So now if I put HA proxy on top of that, basically HA proxy load balances the requests coming to each of the hosts. Now each of these become single point of failures, and I need to make sure that if they fail, I have a good recovery plan. So I can use Pacemaker to form a cluster around those three Neutron services, which present the API, and I can do the same thing with my HA proxy, basically building a Pacemaker cluster around the HA proxy service. So if the HA proxy service itself fails, I have a recovery plan for that as well. And now, again, my VIP for Neutron or for Horizon or for whatever lives in the HA proxy and basically load balances once there are failures. So this is the general approach for high availability, and we use it for the various services. Obviously, we use internal mechanisms for stateful services, and Livnat is going to discuss the Neutron internal services.
Thank you, Arthur. Okay, so what you've just seen by Arthur is basically an external tools that can be leveraged by all the different OpenStack components. What we're going to go over now is the built-in mechanisms in Neutron. One disclaimer before I move on. All the things I'm going to mention are relevant only to the OVS-based reference implementation. So if you chose to go with a vendor solution, you have to go and talk to your vendor for a high availability. Okay, maybe one more thing. In OpenStack, with the reference OVS implementation, you have two different architecture you can go with. One is the centralized networking, centralized network node architecture, and the other one is DVR-based, the distributed virtual router. I'm going to cover both, hopefully, if we'll have the time. Okay, let's look at the component and which processes we have on each of the node and see how we're going to provide high availability to each one of them. So starting from the easy one is the controller node. Basically, we have there the Neutron, MySQL server, and our RabbitMQ server. For making them highly available, we're going to use what Arthur presented, basically HA proxy, monitoring, local restart as needed. It's basically local services that you can use Pacemaker for. Moving on to the compute node, we have the OVS agent and OVS running. Both are local services. Again, no big deal there. You can just monitor them. There's no setup-wide outage that can be caused. So it's local, and you just use HA proxy. Pacemaker, I'm sorry. Okay, so the third one is the network node, and this is the complicated one, and we're going to go over all the services in that node. We have the DHCP, basically, the metadata, the OVS, and the L3 layer. Okay, so let's see what we have. Let's start with DHCP. Okay, for DHCP, actually, we have high available solution in active mode starting since Havana, I believe. It's already out there. We just need to use it. How does it work? It is based on the fact that on the way Neutron today distributes IP addresses. The way it is actually done in a static way. It's not really dynamic, although it's DHCP. When a port is created, an IP address is allocated in the Neutron server itself. It's being associated with the port, and the MAC address, is being taken from the pool. All this association is done on the Neutron server, being updated in the database and distributed to the DHCP agent. So if you have multiple DHCP agents, all of them see the same data. And then the DHCP agents update the DNS mask configuration file, and there you go. You have the same information for all your DHCP servers. The thing is that that's not good enough. You also need the support from the DHCP protocol. Why is that? Because you need to be able to have coexistence of two different DHCP servers on the same pool, serving the same subnets. And actually, this is built in the mechanism. Based on broadcast, the protocol enables that. So if you want an active solution for your DHCP, just go ahead, update the DHCP agent per network configuration, make sure it's more than one, and deploy multiple DHCP agents, and there you go. We have a DHCP agent which is highly available. Moving to the second mechanism that was introduced actually early in the Kilo release, it's the process monitoring. The process monitoring is actually handling a common problem. The common problem is that services are being spawned dynamically by the Neutron agents. So for example, the DHCP agent spawns DNS masks. We have the L3 agents that when you use VRP, spawns keep alive the processes. So all of these are they are dynamic. They are created dynamically, and they are being deleted dynamically, so you can't use, well, it's not recommended to use Pacemaker for such resources. So what do? We talk to Miguel. Miguel Angel Ajo is the Neutron guy that actually coded this feature. And what he did is added a process monitor class that is based on the process manager, and it's monitoring all the sub-processes that are being spawned by the agent. it's turned off by default in the kilo release for backwards compatibility. And basically, it enables, well, you can set 3 actions as a result of killing if the processes die. One is simply respawn them. The other one is kill the agent or exit the agent that spawned them, assuming that when the agent restarts, it's actually syncing with the server data and respawns the missing processes. The third option is notify. It's not there yet. It's based on an Oslo library that was not committed in the kilo release. Hopefully, we'll get that in Liberty. So you've got this feature. You can use it. To enable it, all you have to do is go and check child processes period, update this configuration file to be bigger than 0. And then you have the process monitoring polling for your processes. That's how we cover keep alive D, metadata proxy, and DNS mask. All of these are dynamically spawned and can be covered.
So process monitor is running on compute node, or it's running as part of the network?
As part of the network node currently. This actually, all I'm talking about today is the network node in this processes. So we have the metadata agent, the OVS and OVS agent. All of them are actually local processes that can be monitored by a Pacemaker, like the other processes. So we've got this problem solved. And we're almost there, or not. So we have the L3 agents. That's the most complicated agent that we have. In the old days, what we did is we simply use Pacemaker for it. We restarted the L3 agent when it died, and that was really painful because the failover time was really, really slow. For example, for thousands of routers, it could have taken hours to recover, to get back and running. So that was not acceptable. So what do? You go to Asaf Muller. Asaf Muller is also on the Red Hat team. We worked together with Sylvain, previously in Innovance, today in Red Hat as well. And we asked him to come up with a solution, and this is VRRP. So early in the Juno release, we added VRRP. Let's take a short detour to understand what VRRP means. VRRP basically is a protocol. It exists in the physical world. There's nothing new there. What it does in really high level is provide high availability for a virtual IP address. That means, and for an IP address, it is using virtual IP and virtual MAC as concept to get the high availability. So you have one master. Actually, you have 2 routers serving for the same virtual IP. One of them is the master. One of them is the backup. You can have as many backups as you want. That's the redundancy level that you have in the protocol. You have the sync network between the master and the backups. The master keeps sending a hello message every few seconds, configurable, of course. And once the backup node realizes that it didn't get any message from the master for a certain amount of time, an election process starts, and you have a new master. So this is like really fast how VRRP works. Maybe just one more note. Once the master goes to the backup slave becomes the master and sends a gratuitous ARP message to the physical port and updates the table in the port. And that's the transition is completed. So what we did in Juno is actually we leveraged this protocol by using Keep Alive D. Yeah, Keep Alive D already implemented VRP, which made our life really easy. So what we did is we just used that. We created the network for the sync operation by using one of the tenants network, and that's basically was it. Now it's up to you. You can choose what level of redundancy you want. You just need to configure how many router you want to create when you create a new router. So when you create a new HA router, the system behind the scenes will create actually multiple routers. What is new in Kilo, and that's really important from the usability point of view, is that now you can also get a report which a network node actually holds the master role, which is really critical for you as a network administrator. This is new in Kilo, and there are a few other things that we are actually currently working on. We can say that it's more mature now, and the solution is being deployed in production Actually, for many customers of Red Hat, that's the default deployment that we currently use. So the features we're working on is to make L3HA working with L2POP. Mike Kolesnik here in the audience actually worked on that on the kilocycle. It's not completed yet. We still need to do another iteration. Hopefully, we'll get it landed in Liberty. OK. And monitoring the external interfaces and L3HA plus DVR. I want to skip that because I want to get to DVR, and we are short in time. So what's the problem with this amazing solution? Assuming that you have three-tier application, you have your web application, your web server, your application server, and your database. Classical three-tier application, you have them all on different networks because that's what the US Federation is requiring from you. And you have them deployed just by accident on different nodes. So the way the traffic flows is that for each packet that you want to send from each and every part of your application, you have to do a round trip to the virtual router, which doesn't make sense. So that's why DVR came to play. DVR actually came to solve two problems. One is the optimization of the network flow that we just saw. The other one is to localize the failure domain, which means that the distribution, the routing moves from the network node to the compute nodes. OK, I'll go really fast. OK, so this is the problem that DVR came to solve. DVR is using three types of traffic. Is classifying three types of traffic. You have the east-west traffic, which is the traffic that goes between different networks within a single tenant. Then the traffic does not have to go through the network node. It is just being localized, and the routing is done between the compute nodes. The second type is north-west, north-south. There's no northwest yet. So north-south using floating IP, which means that you want to get your compute node connected directly to the external network. Please note, it does mean you have to rewire your entire data center or do that in advance, but this is something you need to take into consideration. So this doesn't go to the network node. And the last type of traffic, north-south, using SNAT. This is not solved yet, and still we have to use the network node. So whatever HA solution you want to get with DVR, you still need to make sure your network node is highly available, which means VRRP. OK, so let's see what changed in the architecture. This is the original architecture we reviewed earlier. So we added each of the compute nodes is now connected to the external network. We have more services running on the compute node. And basically, we still need the network node. So this is like the way the new architecture looks like when you use DVR. OK, so just a quick closure. There's no one-stop shop. If you want to get a highly available setup, you have to go and use external tools. You need to use built-in mechanisms, and you need to combine. OK, thanks. And you need to combine multiple solutions to actually get a fully highly available deployment. The second thing is that's actually that's a recommendation. You can either choose it or not. But use as many built-in mechanisms as you can when you're going to deploy a highly available solution. And why is that? First of all, you don't get to be a vendor locked in. The same solution that you use using Neutron with one vendor, you can use the exact same solution when you move to the next vendor that provides OpenStack. And that's one of the key aspects of open source, to be honest. So leverage that and use it. In addition to the fact that it gives you the freedom of choice, it's actually also widely used. Because the mechanism is already there. It's for free. Many people are trying it. This is what's gating in OpenStack upstream, which means it is also being tested by default on each patch. There's a huge advantage for using such mechanisms. So it's up to you. You can choose to deploy it or not. OK, that's something. Always understand what you need and use the accurate, the appropriate tools to achieve that. So if you cannot wire each and every compute node to your external network because of whatever limitations you have, you cannot come and ask for DVR. We've got customers asking for that. And it's like a built-in in the mechanism. You have to acknowledge your limitations. This is one thing. Another thing is that if you know what scale you're going to deploy, that could impact your requirement. So if, for example, you're going to deploy 10 hypervisors with 2 routers, maybe you don't need VRP, you don't need DVR, you can just go with a simple, stupid approach of reboot your L3 agent. The failover time would be relatively short. No concerns there, just go with it. And it's going to solve your problem. One thing which is always true, the more complex the solution is, the more bugs we're going to have there. And as an engineer, I can tell you that we do not like debugging HA bugs. It's like impossible to reproduce. So choose the simplest and the one that suits you more in terms of solution. And if you have more questions about DVR, maybe more deep dive questions, you can approach me after the session because we don't have time now, and I'll try to answer them. We do have time for questions? OK, great. So go ahead. Any questions? OK, we already have a solution. We don't have to wait for the future. So you have VRP, which solves this problem, basically. Because the same router is being scheduled on multiple nodes in the same time. So you don't have single point of failure. If one of the network nodes fail, one of the other network nodes take over the role of being master and then serves the traffic. So you don't have any failover time. Well, actually, you do. It's a constant time. The time that takes the backup node to realize that the master node is not active.
Yeah, and the routers are like, so if you have 10 routers, it doesn't mean like all 10 are on a single node. They're distributed across the Neutron nodes. So if one fails, only like some portion of your routers fail, and only they have to be started on the other network nodes.
You need a network node because even if you go to DVR, which is the distributed approach, for SNAT traffic, there's no solution yet. You have to go through a single point in your network because you want to do the nothing stuff. And
it could be physical router and then to the data center.
Yeah.
And it could be this single point, and then to distribute the traffic across all compute nodes. And in this scenario, you don't really need the network node running on separate.
OK, yeah, so what he said is that basically if we combine a physical hardware within the solution, we might be able to avoid a single point of failure. And that's true. It depends on the hardware and how you configure that. But it's the same if you use VRPs. So.
Yeah, it really depends on the reference architecture you're trying to build and the scenario you're trying to build. Right, so I think we're out of time, and we're still around if you have any questions after on.
Thank you.